Alright, so hello and welcome. Howdy. We're going to take a look at another problem today. We're going to kind of jump right into it. Mostly because, I don't know, just want to. I don't have a particular reason to, just going to. So this has 27% success rate, so this is probably one of the hard problems, and a lot of downvotes compared to the upvotes. So people like to upvote the things that they can solve. They don't like to upvote the ones that are tricky. This is almost certainly going to be a tricky one. Almost certainly going to be a tricky one. What we want to do is, I guess, start with reading the problem. Substring with concatenation of all words. You are given a string S and an array of strings words of the same length. Return all starting indices of substrings. Given a string S and an array of strings words of the same length. Okay, S, words, okay. Return all starting indices of substrings of S, that is a concatenation of each word in words, exactly once in any order and without any intervening characters. You can return the answer in any order. Barfu the barman. Barfu the barman. The foo barman. Barfu the foo barman. Words in foo bar. 0, 9. Substrings starting at index 0 and 9 are barfu and foo bar respectively. The output order does not matter, returning 9 0 is fine too. So 0 you can get foo and bar. Okay, I see. So any order of concatenation of these words. All starting indices of substrings in S, that is a concatenation of each word in words exactly once in any order and without any intervening characters. Oh, very interesting. So I see. Alright, there's some ideas swimming around my head what we might be able to do. Neat. Excuse me, interesting. Word good, best word. Word good, best word. Word good, good, best word. So good, best word. Oh, it doesn't have word twice though. Oh, okay. So no good. Empty. Bar foo, foo bar the, foo bar man. Words foo bar the, foo bar foo the. So bar foo is no good. Foo bar the, it works. So that's 6. Foo bar the. You have bar the foo, also gives you 9. And then the foo bar gives you 12. I see. Very interesting. S has 10,000 characters. The number of words, 5,000 words. Each word is only 30 characters at most. That gives you quite a large number. It looks like 150,000 characters in our words. 10,000 characters in S. Words of I consist of lowercase English letters. Okay, 5,000 words though. That's interesting. So, interesting question. Let's ponder it for some time. I don't actually know the answer. I don't know the answer. I will start with saying I do not know the answer to this question. Yeah, and this needs to be somewhat efficient because these are relatively large amounts that we're dealing with, so probably not going to be a brute force solution. So one idea is one approach, not a good approach, but an approach, would be to take every word in our list of words and create the permutation, every permutation, right? So create every, obviously there's way too many of them, there's 5,000 factorial permutations, but take all the different permutations, the concatenations that result from the permutations of all the words, and you can do that, and then you can take each of those words and test the result against this string length to see all the indices where that word shows up. And that also is kind of a challenging question too, because you could have overlap. I think in theory you could have overlap because some of the words in this dictionary could actually have, like you could have food and you could have I don't know, or you could have like bait and baited, right? So both of those words would actually start at the same index potentially. If baited was there, it would actually suffice for both bait and baited. You would need to have bait, baited. I mean, yeah. So really interesting question. Challenging. Probably requires some special string manipulation that I don't actually know offhand, which is kind of annoying. We might have to come back to this problem. Go read about some competitive programming string related questions, but it's definitely a string processing question. And these types of questions are not typically my strong point. All right, so I don't think it's gonna be a quick one either. Don't think it's gonna be a quick one. I'm looking for. I have a. Oh, there it is. Yeah, I have a. What do they call that? I have some paper I can write on here. Okay. How are we doing on time? How long did it take to read that? 6 minutes? Not too bad. Alrighty. Yeah, I don't know. Because that would be too expensive. I mean, you could do that, what I just described. Like, you could get permutation. Yeah, you take all the permutations and check them one by one. And I guess you would go index by index. So that would be pretty. All of that is pretty inefficient, but you can go from index to index, and you could check which indices do each of these words appear. And that's it. Yeah, and just do it that way. And then gather all the results at the end, and you're done. Now, the problem with that, though, is 5,000 words, 5,000 factorial permutations is an extraordinarily large number. Way too large for what we're doing. If there was like 3 words, we could probably do something like that. But if it's 5,000 words, it's a little much. Okay. Well. One idea might be to see, like, if you were to process from a particular, it's like try one index at a time, right? And try from the first index, and you say, okay, do I have any word from starting from that index? Is there any word starting from that index? Any characters that I select? So I guess from a range from left to right. And any of these characters, do they show up in our dictionary of words? Right, you can create kind of like a hash set of our dictionary, and that would be efficient to determine like which words are present at each index, right? Relatively efficient, not particularly efficient. Now, what's tricky here also is that actually the size of our string is, well, actually no, it would be okay because we only have to check 30 characters deep. So in this case, it would be all right. We could do that reasonably efficiently, or we could check 30 characters in from each index to see all the words that could start. Yeah, that's fine. Let me see. So you could do that relatively efficiently. What would you do after that, though? You want to see. Well, I mean, is that useful information? Do we want to do that? Do we need to do that? Well, what you'd want to do from there is then starting at each index. Can you, of the words that can be generated from that index, you could create a map, like a quote unquote, like actually like a state machine. Basically, create another state machine, just like we do with our regular expressions. Create like a quote unquote state machine where the edges between nodes, or I guess a graph really would be like a graph and kind of a depth first search kind of algorithm. I think that's what we're looking for. You would say. I guess it's a form of depth first search. I'm not sure if that's really. Yeah. No. Yeah. Okay. I'm just thinking. Yeah. Yeah. Depth first search works. backtracking algorithm. So, so what you would do is you create sort of a state machine from each index, kind of a state machine where, I should say state machine. You create something of a graph where you have an index, and that index you can jump from one spot to another if and only if, I guess it's directed. You can jump from one index to another if there's a word at that index in our set. And so you would know what that word is, and you would know where you would jump to. And the idea is that if you can make jumps in such a way that either there are jumps, in other words, like if you can make jumps in such a way that you used all of the words in our list exactly once to make all those jumps, then that index that you started at is a solution, right? Is a solution. If you cannot do that, then obviously that would not be a solution. So it's sort of a Boolean check that we'd have, and for all of those, so you'd have sort of a Boolean check. You go from every index it's possible to go from, and you would update your result set with if it's true that you can get through. Now the tricky thing about this is I don't think that this algorithm would be efficient enough. Part of the problem is you can't actually memoize any of this because of the state that you're using is dependent on, because we're trying to avoid the order, part of the state that we're using is which words we've used up to this point, and basically that becomes like a 0 or 1 kind of a thing. Either we used this word or we didn't. So it's as if we had 5,000 independent variables, I guess, quote unquote independent variables, each of which could have a 0 or 1. So you could have two different values. So you'd have 2 raised to the 5,000th would be if you were to memoize this, which is a very large number. So basically memoization doesn't help us at all. We end up with still end up with an exponential time algorithm. Yeah, it's kind of tricky. It's kind of tricky. You could maybe try something different where I'm thinking maybe some kind of a quadratic time algorithm where you could say in a particular range you have certain. I'm actually trying to think of like how you could optimize that, but no, quadratic time is too slow. But you could go on every subset, check to see. No, that doesn't really work either. I mean, that's the same question though. That's not really no. Yeah, I don't know. I don't know the answer to this. I don't know. I'm sure there's some kind of string manipulation thing. I guess we'll probably look at the discussion for this one afterwards and see what's there. Huh. Mm-hmm. I guess one side of this is like, because these words are so different, it's very likely that our algorithm, even though in the worst case could be very slow, technically could be very slow. I guess what I want to say is that actually in practice it won't be that slow. Probably because you just won't have that many different possible choices for each jump. Yeah. Like if you only had one choice at each jump, then actually the algorithm would be very fast. It would be basically, excuse me, almost what is that? I guess it'd be 10,000 times 30, right? Sort of big O of the length of the string and times the size of the maximum size of the string in our dictionary. Yeah, that's it. But that's in a very fortuitous case where that actually only really works when your words in the dictionary are distinct from each other. In other words, they don't have any. They don't start with this. The prefixes of each of those strings are different from each other. But when those strings have prefixes that match, that's when you get into some trouble. It's actually not even the prefix. It actually has to be, the strings themselves need to be substrings of each other in order for the algorithm to be anything more than linear. So yeah, I guess it is okay to do it this way. Yeah, I'm just thinking about it because at first glance doesn't seem to work, but actually upon further inspection you realize that you only run into issues when you have words that are prefixes of each other. Words that are, yeah, when one word is a prefix of another word. And it's kind of unlikely that you'll have that in most cases. However, you could try a dictionary of just all A's and all strings of just containing A, the character A, and then each of those strings of different lengths. So from 1 to 5,000, that could be your dictionary. In which case, everything is a prefix of everything else. So at every point, you have 5,000 options to jump from in your graph at each index. Huh. Excuse me. Can we optimize that? I guess one straightforward optimization is we could also just count the number of characters we need for the string to exist in the first place. And we don't have enough characters, we could terminate early. There's that too. I don't know if that's really useful here though. Excuse me. That's a good use case to consider, just if you had 10,000 A's and then those 10,000 A's split up into a whole bunch of different strings, how would you handle that case? Have these different prefixes you could use. You might suggest, well, you should use the, that really throws a big snag into the whole question, the whole problem. Because you might suggest something like, well, why not use the longer, the two strings? Because if you use the shorter string, that means that suffix needs to also be the prefix of another string. And that won't ever be a concern. Like, in other words, you could argue that, like, well, maybe you do need to consider both jumps, but when doing that, you'll realize that the jump that won't work will fail immediately because the suffix to your string isn't a prefix of another string. But actually, with all A characters, it is. Right? If they're all just A's over and over, you could kind of probably pretty easily break up, a string of 10 A's into two strings of five A's. Yeah, it's very interesting kind of edge case that opens up kind of a Pandora's box. For the majority of cases, it's probably not an issue, but for that particular case where you have a lot of overlap between your dictionary words, that can cause some problems. The algorithm could slow down quite a bit, trying to try all the different possible, I guess, permutations really would be. It is also interesting because in that case, it would actually be the first attempt you make would succeed or fail, which is kind of ironic, even though you'd have a lot of different possible ways this could be done and looked at through the algorithm. It would just immediately succeed or not be possible, I think. Yeah. Well, then you could consider like lots of A and B, two characters A and B, and a lot of mixing there, a lot of overlap. Where you would need to be a little bit more discerning in how the algorithm is actually executed. I'm trying to think of a test case. Actually, yeah, that's an interesting test case because that test case what we gave as the algorithm would actually terminate. No, I'm sorry. Yeah, actually, it would be fine. It would just say every index probably would work. No. You would run into a problem where at some point the indices. Well, no. I think every index would work. I think it would just be every index works until. No, yeah, that would be actually kind of efficient. That would be overall relatively efficient. So you get the number of words in the dictionary times the number of indices, which is 5,000 times 10,000. It's actually kind of a lot, now I think about it also, by the way. Well, yeah, kind of. I don't know. I don't know, man. It's kind of hard. That might time out. Yeah, 5,000 by 10,000 is 50 million. It's kind of a lot. Kind of a slow algorithm. I guess that's one instance where the memoization would be helpful. I don't think so, though. This is a tricky problem. I don't know. I don't have a solid solution here. Wondering if maybe there's like some set of words that you can use. Thinking maybe like a divide and conquer algorithm. I don't think so. I don't think a divide and conquer will be too useful here. Maybe a stack-based solution would be useful. Hmm. Hmm. Excuse me. Well, actually, I take that back. There's not 5,000. There's at most 30. I guess the branching factor would be at most 30. 30 possible words that you could have from a particular position, excuse me, to the next position. And I guess also it would be you can only use words you haven't used yet. I guess you could maintain like a frequency map of the words you've seen. Have to use exactly one of every word. I don't know. I mean, maybe this is not as bad as I think. How deep would you go if you had? Well, no, you could go pretty deep if you have 10,000 letters. Maybe you could do a little bit of quote-unquote memoization by going from right to left, and you would say, at each of these indices, you would know which pairs of words were possible to use, and then I guess from there you'd be able to figure out index by index, because you know which concatenations are possible. You can kind of take the differences in the frequency maps, quote unquote differences in the frequency maps, to check quickly at those points. That's a kind of memoization. I don't know if that makes any sense though, if that works. Yeah, because, well, yeah, I mean, you get like partial mappings that way. You can maybe do something like that. Get the partial mapping of every index from right to left, and that would allow you to know. Again, there are a lot of. Maybe that's not true. Maybe that's not. There aren't that many possibilities. I don't know, man. The partial mapping. So the problem with that is, yes, you can avoid doing work again, I suppose. I'm trying to think about that. Like, how do you? It's not the same thing as storing the answer and returning the answer directly, but it is a way of. I guess you would have the whole set of possible. I guess at each. Yeah, okay. I think it makes sense. So you can say at each index you have a whole set of possible partial frequency maps, and to process that index from wherever you came from to that point. So you have a frequency map already you've built, and you would check, does this match any of those frequency maps? Actually, do any of them? Yeah, I mean, you do matching. It's really if you added the two frequency maps together, do they equal to the frequency map that we built of the dictionary originally? And if they do match, then that's a solution, right? You found a solution. If they don't, you found an index that's or whichever index you came from is the solution. If they don't match, then that node you would stop at. You actually would not continue from there because it's impossible at that point. You would actually just stop. So you would stop processing that at that point. Now the tricky thing there is that each of those frequency maps, if you try to match them against each other, they have 5,000 elements. So at every point you'd be doing 5,000 times the number of possible solutions, partial solutions that exist there, which is not a small amount, potentially. So the number of partial solutions could be, well, actually a lot of them, all of the permutations would just be one frequency map, so that's not really a problem. How many frequency maps? But there could be a lot of frequency maps, right? There could be, if every character had another, well, no, there's only 26 characters, so actually it's not really possible to be, well, 26 cubed, I think, is more than 5,000, right? So you could have 3-letter strings. Let me think about that for a second. 3-letter strings, is that right? I think 26 squared actually gets us. Yeah, 3-letter. Yeah, 3 letters. Yeah, 3 letters enough. 26 cubed is definitely like over 5,000. Because I think 25 squared is 625, and then 26 squared is then larger than that, and then multiply that by 10, you're already over 6,000. So yeah, so you could have 3-letter words, and I can give you 5,000 of those, and then if depending on how many characters you have to the right at that point, let's say you had like 5,000, so then you could do 5,000 divided by 3 is somewhere around 1,300, right? A little over 1,300, 1,350 words, and basically you have every frequency map is sort of a 0 or 1. Either you have that word there or you don't in your frequency map. So you have sort of each frequency map sort of has 1,300 entries with the 0 or 1 to the right of it, which gives you 1,300 of, which is actually a lot, right? There's a lot of different. That gives you an exponential number of possible frequency maps. It gives you 2 raised to the 1,000 different possible solutions at that point. Which is a lot. I realize that's a lot. Yeah, that's a lot. Do you just build a set of frequency maps? In other words, you take all of the frequency maps you already have and you just add this word to those maps? Maybe that's what's supposed to happen from right to left. Maybe you're not supposed to do what I just suggested. Maybe it's as simple as you just accumulate all these different frequency maps from right to left, and then at the end, you just check if any of them match the target frequency map. I mean, I guess you could do that. You could also preemptively eliminate maps that definitely don't, that either have, just have too many of a certain word counted, or just, I guess, quote unquote, not possible to, not quote unquote, but just won't be able to make it, maybe, I don't know. How do we do this? It's probably gonna take us a lot more than an hour to solve, I think. I think so. I think it's gonna be one of those problems that we break up into multiple pieces. Yeah, I mean, you get some frequency maps, right, at each index, partial frequency maps. And then for each of those maps, if there's another word, yeah, I mean, basically what you would do is at each index so we're going from right to left, and we're going to look at the characters from that index from left to right. So we assume we have all these frequency maps already developed. If there's a word in our dictionary from left to right, we go 30 characters in. If that word is in our dictionary, then we can say, okay, check if there are any frequency maps that exist at the index that we end up at, that we've already computed, and we're going to add this word to all those frequency maps. And I guess there's sort of always a default frequency map of just nothing found, just all zeros initially. So we add one to each of those that exist, and we make those part of, and we take the union of all of those results for all of the words that can be found at that index, right? So we would get, a union, and actually make a set. So any frequency maps that match each other, we would just throw out, right? We just keep the same ones. So we wouldn't have duplicates of those. So that would handle the permutations. The problem with that approach, I think, is that our sets of frequency maps, I want to say they'll grow exponentially. That's, I think, part of the issue. Another problem with that too is we also have issues. It's not just that they'll grow exponentially, but also this only works for if we finish on the rightmost character. In other words, we'd have to run the same routine for every index from right to left. That's another problem. Can't just do this all in one shot as well. So one, I don't think it even works just from. I don't really. No, I don't. Don't think it works. Don't think it works. I'm kind of thinking maybe there's a divide and conquer kind of approach to this, where you can split on every index and kind of decide, what can be found to the left of this index from right to left, and what can be found on the right of the index from left to right, and then can you combine those pieces? And they're different problem. Like, it's different. They're not exactly. It's not exactly divide and conquer. I don't know about that though. It doesn't seem too good. Doesn't seem too good. Also seems like you probably could just run the left to right routine from left to right on every index and do it that way as well. And just not have to cut anything in half. There's that too. I don't know. I'm gonna lay down. I don't know. I don't have a solid solution to this one. I gotta really ponder it for a while. Oh. Oh boy. Let's think about this for some time. Let's think about this for some time. From left to right. What kind of an algorithm can we use? It's tricky. Part of the issue is trying to memoize this is very tricky. Hmm. Yeah. Also, one issue is that if we try to run any kind of algorithm that takes quadratic time, I think it'll take too much time. It's 10,000 squared is kind of a lot. It's 100 million. It's probably a little too much. Hmm. Oh wow. Close my eyes and I start daydreaming almost immediately. I must be very tired.
Oh man, I mean, I was just pondering this question probably for 20-30 minutes now. All that pondering was just to, I don't even know what it was supposed to do. I think it's, actually I don't think I necessarily got anywhere with that. Still don't have an answer. Still thinking about it. Alrighty, I got stuck on this problem. I've been thinking about it for a few hours now, I think. I think it's safe to say I got stuck. Yeah, the brute force approaches don't seem particularly good. And memoizing doesn't really seem to help much either because of all the possible ways that each of these. No, even the permutation. It's really just all the different ways you could have. I guess some subarray, sub consecutive subarray, we'll say. How many different ways? I guess you could use all of those characters to get call it a frequency map. How many different frequency maps you can build? I want to say there's a lot of different maps you could have. I think I'm maybe making this problem out to be harder than it is. I think that's one of the issues. Like I think maybe one of the just like a simple approach actually gives you a reasonable running time. I try to think that one through for a moment here. Let me try to think that one through. Excuse me. I'm gonna put the headset down though while I'm kind of just laying down and half falling asleep and half thinking. man, totally unrelated, but my feet are really itchy because of I've been standing lately. I'm a standing desk for maybe like a couple weeks now, and I've been one of my feet are getting like sore because I'm just standing on them so much. And I thought it was gonna kind of fade away after a week or two, like that my feet would kind of like get used to it, but they haven't, and I'm kind of like, well, one, they're itchy, but they're also I don't really understand why that is. I was kind of expecting my feet to sort of adapt after a while, but yeah, so you're gonna hear me like moving you might be able to hear that, my feet moving around, just so you know what that is. I don't know if you can hear it from there where I put the phone mic, but maybe you can. headset is running out of battery. Wow. I gotta charge it. I don't really have a solution to this problem, man. I'm keep thinking about it, but I'm not really getting too far. Well, I could charge my headset. Also, I think I gotta use the bathroom soon. I don't know, man. I don't have a solid solution to this. I'm thinking about, like, maybe you could do something with, like, if you just went through a bunch of test examples, maybe you come up with something it would kind of resemble what you would do. I'm thinking, like, the problem seems to be, like, so if you had a solution, clearly you can sort of swap a string from the left side to the right side and kind of make like a treadmill type of thing. Not treadmill, but yeah, I guess like keeps like removing a word but adding it to the appending to the end. The same word, like you can know that that's those are also solutions. Something like that can work, but I'm wondering what the limitations of that is. I guess the first thing, and then also, like, how would you get the first solution to begin with in the first place? I guess you would, like, from the first word, see if you can get a word from the dictionary for the first index, and then I guess if you can't, check the first 30 characters. If you can't, then you go to the next index and you kind of do that from left to right, and then you see, I don't know, man. That's a tricky approach. It's also potentially quadratic time, which is too slow. If you do this, like, from each character index, and you just kind of try to go left to right, grabbing all of the possible words. I don't know. It's kind of challenging. It's a little bit challenging here. I suppose you could do kind of what I was describing before with the graph, where you kind of just jump. You sort of have predetermined, which words fit at each point, and you can kind of jump. But problem with that is that you could end up reusing words. Like, I think I was saying that before. You end up reusing words. You could also have words that are related to each other. So then you get into kind of hairy territory there, like either prefixes and suffixes and things, in terms of which words you should use. Because if you use a shorter word, you might not be able to, or use one word in one spot, you may not be able to get all of the words. After that, so you gotta try a different word at that spot and see if you can still get all of the words. You still can use all of the words. I don't know, man. I don't know. That's difficult. It's challenging. That's a challenging question. I don't have the answer to that. Trying to think of something that's like relatively efficient that's also correct. I don't think I have one. Because the things that explore multiple options end up being like backtracking of some kind. And I think backtracking with the bounds that we're given here, it's just not going to work. Like, it's just going to be too expensive. That's the thing I'm struggling with right now. That's what I'm struggling with. I'm thinking maybe this is why it's got so many downvotes. Maybe you are supposed to back. There are some questions like that I've seen on LeetCode where ultimately you're supposed to backtrack. And it just so happens that the backtracking algorithm is efficient enough for that problem. I have actually seen that before, where that is what you're supposed to do.
And there really isn't a much more clever way, and it just so happens that the test cases that they give you are efficient enough, but in general there could be actually test cases where it would not be fast enough. That's a tricky thing. I've seen that before. That could also be why it's got so many downvotes. I don't really know though. I don't really know. Continue pondering this. I don't really have much to say other than I think I'm kind of stuck here. Let me keep thinking about it for some time. So actually, I think I'd use the bathroom. So I think I'm going to stop here. How long we've been? Yeah, in a couple hours we'll look at this. So I've been thinking about it. I think what I'm going to do is I don't have a solid solution. I'm just going to say. I think we'll stop here. I need to use the bathroom. What I'm going to do is maybe try to think about this a little bit more and maybe try some like problems by hand. Let's see if I can come up with something that's like relatively efficient. But I really don't have a solid solution, not yet. Yeah, unfortunately, I'm not entirely sure how to solve this one. Yeah, yes. Yeah, so we need concatenation of all the words in any order without any characters in between. And we're going to count every index that starts that substring. Very interesting question. Not. I'm wondering if you could modify certain string search algorithms to see if they work for this. Like a K&P algorithm, something like that. I mean, you could use like a modified string search algorithm that doesn't like there's a version of the K&P that's slow. Like K&P is O of n plus m, where n is the larger string and m is the smaller string. But there's also a version that's O of m times n, right? Which is not the same, but similar. And like maybe we can get an algorithm that's slow, and then maybe we can find a way to optimize it, kind of a thing. But I don't even have like a slow algorithm that's reasonable. This is a kind of a substring search, but it's like it's a special kind of a substring search. I don't know. I don't really know what to do with this problem exactly. But what I'm gonna do is I'm gonna use the bathroom and then come back. So thank you for watching. I will talk to you soon. Yeah, I didn't go with anything good. We'll come back to this. We'll try again. All right. Take care.